Hello everyone! Welcome back to another episode of Simple Harmonic Motion. In this video, we'll be talking about how to derive the x function, or in other words, is basically the displacement function of simple harmonic motion. Okay. So without further ado, let's get started. Also, on a side note, I'll be using a bit of circular motion concept to derive this. And this is not the only way to derive, it's just I find this way easier to visualize and understand, so I'm going to show this way. Okay. So I have drawn a circle, as you can see here, with radius r. And what I'm going to do is, I'm going to show you the motion of this blue dot. Okay. So initially, the blue dot is at equilibrium. Okay, I'm going to label, this is too big. Okay. I'm going to label this point as equilibrium. EQ means equilibrium. Okay. Now, let's say for after a certain amount of time, the blue dot moves to this point. Basically, it moves through a certain angle after a certain amount of time. This line here is radius r, because the distance from the center of circle to any point around the circumference of the same circle gives you radius. Okay, I'm going to label this as x. And just now I said it moves through an angle. The blue dot, after a certain amount of time, it moves through the angle, and I'm going to label that angle as theta. And this, if you can see, is actually a 90 degrees triangle. So now what are we going to do is I'm going to show you the motion of this blue dot from equilibrium position to this point. I'm going to show you the motion of that position. Okay. So here we have a right angle triangle. Whenever we see a right angle triangle, we know we can use Pythagoras theorem, right? Okay. So from here we can see that we can say cos theta equals to x over r, because cosine is adjacent over hypotenuse. Our adjacent is x. Our opposite side is x. Sorry, it's not cosine, yeah? It's sine. Sine is opposite over adjacent, and this is opposite. Your opposite is x, and your hypotenuse is r, so it's x over r. Yeah, sorry, it's not cosine. Yeah, it's x over r. Okay. So, since we want to find the function of x, let's try to make x as the function, x as the subject of this equation. Okay? So, we will have x equals to r sine theta. Now, can we refine this equation even better? Yes, we can. So, how can we do this? Okay. Just now I said this is my equilibrium, right? This point here. Not this point, basically this whole line is my equilibrium position. And this point to this is my x, right? That is what I've labeled on the circle diagram as well. Now, what about from this point to this point? Based on the diagram, I have said that it's the radius. But is there another quantity that we can use? Yes. This point here is actually, not this point, this line here, your radius basically, is actually your amplitude. Now, why is it your amplitude? Okay, initially it is at equilibrium, right? It's at equilibrium position. Then, from equilibrium position, it moves up to the highest point. When it moves up to the highest point, it is actually moving through a distance of the amplitude. Okay, I'll draw you the graph, then I think you might be able to see it better. Okay, so this is, we have a graph here. This is x, this is the time. Okay, initially it was at equilibrium, right? It was at equilibrium here. Then it goes, after a certain time, I said it reaches this position. Then it's going to reach the highest point, which is, this is the highest point. Then it's going to go down. It's going to come up back. Okay, I'll show you the motion. Let me draw the blue dot here. Okay. Initially, the blue dot was here, right? Then it goes up here, which is this position. I say after a certain time, it goes there. It doesn't have to be specifically there. You can, of course, it can be here, it can be here, up to you. I just say that after a certain time, it's at this position. Okay. Then, after that, it's going to reach the highest point here, which is actually this point. I know it doesn't look straight, but you get the idea, right? Yeah, it reached the highest point. Then, after that, the blue dot is going to go down here. Now, where is this position? This position is when the blue dot is here. It's at this. Then, it goes down to the lowest point. Now, where is the lowest point? It's actually here. Then, back to equilibrium, back to this point. So that is why I said from here, which is the equilibrium, to the highest point, it is actually the amplitude. And when we draw it in the circle, it shows the radius of the circle. Okay, CIE will label the amplitude as x0, but you can also label it as A, which is to show as amplitude. Up to you, it doesn't matter. The main thing is, when you plug in your values in the equation, you must get the same answer for both, using x0 or amplitude, which is A. Okay, I'm going to use A in this case. So x equals to A sine theta, or x equals to x0 sine theta. A is basically because it's amplitude, so I just took the first letter A to show that it's amplitude. You can use x0, also can, no problem. Same answer. Okay. Is there something that we can further refine this equation? Yes. We can actually replace this theta with something. We know that theta equals to, not theta, sorry, omega equals to theta over time. We have learned this in circular motion before. So what is theta? Theta is omega multiplied by time. Can we sub this inside here? Yes, we can. So our final equation is x equals to A sine omega t, or x equals to x0 sine omega t. In your formula sheet, you will see this form of equation. So this is our final equation for the x function. You must know this. They have never really asked you to derive it in exam, but of course it's good to know a way how to derive it. At least you understand where the x function comes from. And another thing to notice is, if you realize, the graph I draw here is actually a sine graph, right? And it is consistent with the equation that we just derived. It has a sine function as well. So usually the graph and your equation will actually be related. If you have a sine graph, you most likely your equation in x will be a sine function equation. Yep. Now, is there a way I can do cosine function? Of course, there's a way. It's just the motion will now not be from equilibrium to this point. It will be a different motion. So the first part, we saw the motion from equilibrium to a certain point here. That means it's from equilibrium moving up. Now, to derive the cosine function, we will look at a second type of motion. So now, let's say after a certain time, we see that the blue dot is at here. Now, we're going to see the motion of the blue dot from this point to perhaps this point after a certain time. Your equilibrium is still here. It is still here. It is still this point. What I'm saying is, in this second scenario, we're going to see the motion from this point to this point. Now, how do we do that? It's the same concept, same way that we derive the first scenario. This point to this, it's your radius, right? Okay, I'm going to erase this R. It's your radius. Let's form a right angle triangle. This to this is our x, a distance of x. Remember, the distance x is measured from your equilibrium position. So since we already measured our distance x, I'll just measure here as x, so that it's easy for us to draw the graph later. Okay. And this is our radius, remember? From the equilibrium to the highest point is our radius, which is the amplitude. Okay. This is our angle theta. It has moved for a certain angle theta after a certain time. So, we can use Pythagoras theorem, we can use cosine, and now we can use cosine because cos theta is equals to adjacent over hypotenuse. Our adjacent is x and our hypotenuse is r. So if we rewrite this, it is x equals to r cos theta, and we know our r is the amplitude, cos theta is omega t, or you can write it as x equals to x naught cos omega t. It's the same thing. Yeah, so it's the same concept that we use in the first scenario. Now, how will our graph look like? Okay, so I'm going to draw this. This time. Okay, so initially it start at this point, right? Because I was saying that we are looking at the motion from this point to this point. So it's like here, then it goes down here, which is, okay, maybe not too low. It is somewhere here. It comes to this point. Then it will go all the way down here. It will come up here. Okay, I'll show you the motion with the blue dot so you can see it better. It was here initially, right? Basically here, highest point. Then it goes down here. I said it goes to reach this position after a certain amount of time. It doesn't really have to be there. It can be here also. I'm just randomly picking a point to derive an equation. Okay. After that, it goes all the way down here. What point is this? This is actually your equilibrium. Because remember, the green line here is your equilibrium. So that means the blue dot has reached this position. Now, from here, oops, okay, wait, let me erase the yellow so I can't move my blue dot. Then it goes all the way to the lowest point. Where is this lowest point? This lowest point is actually here. I understand that the line isn't really straight, but you get the idea, right? Lowest point is here. Then it goes up here. Where is this point? Equilibrium. Comes back up here. Then, oops. Okay. Oh my god. Okay. Then from here, it goes all the way up back. Where is this? Back to its position at the highest point where our motion started there. Okay. And what function graph is this? If you realize, this is actually, that is too big. Okay, cosine graph. So our function must also be cosine, which is correct. So that is actually how you derive x function equation. It might be a bit hard to just see it here, like just see from the circle itself how the function works. So I would suggest you to draw the graph here, because I think the graph would make it easier for you to visualize how it works. So when it started at equilibrium, started at this position, we had a sine graph. When it started from the highest point, we had a cosine graph. So what if we started from this point? Yes, you can derive an x function from that point as well. Okay, let me show you. Since we're already at there, let me show you how it works. Okay, I'll draw a circle. Radius, okay, that is not center. Have a center. Here, this is our equilibrium. This is our indicator. Okay, so let's say the blue dot was at here, and now we're looking the motion of blue dot from this point maybe to here, to this point. This is R. This radius is also R. Let's draw a right angle triangle. So this is your right angle triangle, and this distance from here to here is x. I'll erase this R in case it confuses you. Distance from here to here is your x. So it's here to here is your x. And the distance from equilibrium to the lowest point is your amplitude, or your R. It moves from here to here for a certain angle. So can we derive this? Yes. What function should we use now? Should we use sine or should we use cosine? We should use cosine because we have adjacent and hypotenuse. So cos theta equals to adjacent over hypotenuse. Wait a minute. Our x here should be negative. Why negative? Because if you remember from my previous video, I said that, but that was about spring to the left and right. Remember I said equilibrium to the right is a positive x. To the left, it's negative. Right? Now, if the motion is in the circle, so anything above this equilibrium line is positive. Below it is a negative. Shows the negative displacement. So, we should have negative x over r. When we rearrange this, equals to r cos theta, x equals to negative r cos theta. So should we find this, you'll get a cos omega t. So how would our graph look like? If I draw the graph, you would actually understand why is it negative. Okay, let's choose a different color. What color do we have? Okay, we don't have that much of color actually, but okay, let's do it green. Okay, xt. It was initially at here, right? Which is this point. Then it goes up here to a certain point, which is this. That'll go all the way up. That's gonna come down here, but okay, let's see the motion. Initially it was at here, the lowest point. Then after a while I said it moves here. Then it's gonna come here. Where is this? This is your equilibrium position. That's gonna go all the way up. Where is this? This is this. Here. Then come all the way down here. Where is this? Equilibrium position. Then it goes all the way down back to where it came from. come back here. So this is actually an upside down cosine graph, which is a negative cosine graph, because that positive cosine graph looks like this. So if you negative it, it's going to look like this. So if you look at our function, we did get a negative cosine graph. So it's correct. So anything below equilibrium, in this case, is negative. Above here, like whatever we saw above in these previous two scenarios, we let x is positive. Okay, so yes, conclusion, that is how we derive x function using simple harmonic motion. Is there a tangent? No, not really. We don't have a tangent here, because mostly we will have the value of hypotenuse, adjacent, or its opposite length and the hypotenuse length. So we don't have tangent, but we have cosine and sine function. So these are the three scenarios. It's good to know how to derive so that you understand where the function comes from. So that's about it for today's video. I hope it helps you understand better about this x function. I'll see you in the next video. Thank you for watching. Bye bye.